Okay, today's review is coming from Unit 12, logs, and we're going to back up and just show you, we're going to be doing logs and linear programming today, and that's a big day, but I think you'll remember a lot of this. The logs might be a little bit more challenging than the linear programming, but let's start with logs. So if I say 5 to the x is equal to 12, you know there's some power you could put 5 to that would give you the answer. 5 to the, I don't know, let me think. Is 5 to the second too big? Is 5 to the 1 too small? Then it's obviously 5 to the 1 except a little bit more, like 1 point something. And how could you get it? With logs. So everybody try to remember how to write this as a log. Log base something, like log base 9 of 4, except that's not it. Figure out how to write this as a log problem. Then, just for kicks, grab your graphing calculator and figure out, if you remember, how to put it in and get the decimal for it. And the decimal's like 1.67 or whatever it is. Get it to a couple decimal places. All right, I'll pause for a second while you write the log for this and see if you remember how to put it in the calc. Okay, if you knew what you were doing, this should be already done. Logs base 5, because why? Because that's a base, and that's the power. Log base 5, and then if you remember, we never just go in order. They aren't that simple. It's just not log base 5 of x. It's log base 5, and then you jump over to the other side. You bring in the 12, and then you jump back equals x. So there's your little log statement, and it's got two parts. It's got its base and its, what's that called? It's called the argument. Okay, the base and the argument. This one's a base, this one's the argument. It's a BA. All right, so anyway, it's got an exponent also, and this is the exponent. It's extra BA. Because this is the exponent, and notice the exponent ended up being over here. That's why people will say sometimes that logs are exponents. If you're doing a log problem and you get an answer, what you have found is the exponent. So let's figure out what the exponent is. How do you put that in the calculator? Unless you have a calculator that's got this special mode where it can do base 5, and a few of you do. If you've got that calculator and you know how to use it, awesome. Otherwise, you can type in log 12 over log 5, and it will give you the answer. And you'll have to put in the parentheses in the right spots there. Make sure you close the parentheses on this log 12. Otherwise, you're doing a log of a log, and it'll get all confused. So see if you do this right, and I want you to compare your calculator's answer with the person next to you. If you don't get the right thing, it's because you screwed up your parentheses probably. Okay? Compare with the people rows 1 and 2, rows 3 and 4, rows 5 and 6. You're going to do like a little triangle thing there. I'm going to pause while we try that. Okay. You should have had a decimal of, yes? Good enough. And that means if you had put 5 to the 1.54, you would have gotten about 12. Okay. Why wouldn't it be exact? Because it's rounded, and therefore it's not going to be exactly 12. All right. So let's go back to what else can you do with logs? If you had log base 3 of x equals 12, you'd be able to solve that. Try to solve it when there's that x is in the argument spot. Now, I made it really, really big, so I'm going to make it a little bit smaller. Instead of 12, let's say 1.2. You can just put a dot in your 12. Log base 3 of x is 1.2. Solve. The x can be in 3 different positions in logs. It can be in the base, it can be in the argument, which is the one I just did, or it can be in the exponent spot. Did you rewrite this as 3 to the 1.2 is x? That's what you should have done, and then you realized, oh, I just put 3 to the 1.2 power. And what did you get? 3.73. All right, cool. That means if there had been a 3.73 here, log base 3 of 3.73 would be about 1.2. Again, I say about because we rounded. Yes? So this was it rearranged, and the answer it gave me was this. So that means that is x. So I stick it in 4x right there to just check if it actually worked. Okay, next one is log base x of 2 equals, let's say, 10 on this one. Once again, if you can just rewrite it, it always comes down to, can you just rewrite it so either it has logs in it or it doesn't have logs in it. So in this case, I want to get the log out of there. So I do a rewrite. So to really test if you can rewrite things, I'm going to do it with all variables in a second. But this you should have said x to the 10th equals 2. And then how do you fix that? Put it to the power of 1/10. And this becomes 10 times 1/10, which turns into 1. And that means x to the 1, which is just x, equals 2 to the 1/10 power. Would you agree that's the exact same thing as that? The 10th root of 2? It is. And then that's some decimal. Mr. NC, what'd you get? All right, good enough. Okay, that's 2 of the spots. Here's the third spot where the log can, or the x can be. And the weird thing is, it's already solved. Why? Because the x is already alone. Get what I'm saying? This is the answer. And then as long as you know how to get that with a calculator. The only thing that I would say in this is the context of this. Do you get the base right now is 3? Yes. What if they say, I want you to make this base 10? All that means is put it in the way that you'd put it in your calculator. Because base 3 won't go in a calculator, but if you go like this, do you really put it into base 10 by doing that? It's like I don't have bases. Do you remember that? That if you don't have a base, you really have a base of what? All right, so that's a base change because technically this was a base 3, now it's a base 10. What if I wanted it to be base 33? Yes? Okay, hold on just a second. Not the one that's on the board right here? Okay. So this one, if I wanted to be base 33, I just make it a base 33. You can make this, through this base change method, you can make it any base you want. Weird but true. Now, your calculator wouldn't be able to solve that one for you because it's base 33. Calculator can't do that. What is one other base your calculator can do? E. Remember what key that is? The ln key on your calculator. So remember, since we can change this to any base we want, we could make it base E. And therefore, use ln and try this. ln2 divided by ln3. And I think you'll find it's the exact same thing as regular log 2 over regular log 3 would be. Because the bases, as long as you got one on the top and one on the bottom like that, the bases are getting bigger or smaller together. And therefore, the ratio is staying the same. Not really canceling the E, but it means that the E could be anything. It could be 10, base 10, it could be base E, it could be base 145, anything you want. The answer will still come out the same. Because if you get a really big base, then you get a smaller and smaller answer, or the H answer is smaller and smaller, but the top is smaller and the bottom is smaller so that they stay the same proportion. So it doesn't matter what base you use. So that's called base change. All right, so what about this? Log e to the third. I already know the answer because I remember a trick. What did I say every time you saw? Oh, I'm wrong. I'm sorry. I was thinking ln when I wrote log. There. And I was thinking remind them about how, if it's an ln, they should rewrite it as log what? Base e. Good. So this is log base e. Now do you see that those two are the same and therefore the answer is that guy? All right. So the answer was just 3 for that problem. The original problem was this, ln 3. And sorry, it wasn't. It was ln e to the third. Sorry, my brain's not functioning properly right this second. All right, so the ln turns into log base e. And then I have e's here and here, and that makes the bases the same. Therefore, that's the answer. Here's another example of the bases are the same. What do you mean the bases are the same, Mr. Server? Well, the base here is 5. The base of that log is 5. And do you get this is a base in itself? Because it's the base having this exponent on it. And if the bases are the same, then the answer is already there. And the answer in this case is 12. Now, I could prove that to you by a long, complicated process, but this is a review day, so I'm just trying to review things really quickly. Don't have time to reteach you all of it. These numbers are the same, the answer will be right there. If these numbers are the same, then the answer is right there. So if the bases are the same, see this is the base of the log and this is the base having this exponent on it. Those are the same. The answer to this one is 5. Do you get why then? I could say what's x got to be? How come some of you knew it was 3 so fast and other people didn't? That whole thing inside the blue box simplifies down to what? So then it's really x times 5 equals 15. And if you see that really quick, it's like, oh, well then x has to be 3. Yes? Log 3x. You can't, there's no such thing as log 3x. What do you mean? Log base 3 of x. Anything. Sure. Yep, 3 to the 1.2 equals x. That's the rewrite of it. Yep. Or somebody else had a question about a prior problem. If you still have it, ask me. Yes?
So it was the
I'll never find it, but just read it to me. Log base x. All right. And that was, again, x to the 10th equals 2. Good question. Why wouldn't it be plus and minus? Because you're putting something to the 10th power. Here's the problem. Do you get that that the bases aren't allowed to be negative? So even though I get what you're saying, if I put in a -2, it would act just like, or a negative answer, it would act just like a positive one because it's being put to the 10th power. But in logs, this number and this number, both of these, can't be negatives. And they can't be 0. That's a good point to bring up. Thank you for bringing it up. All right. One more thing about logs is that you can expand and condense them. And so do you remember this? Log of 2x could be split into log 2 plus log x. Does that ring a bell? Things that were multiplied can be split up into add. All right. That's something that you're going to do more of in pre-calc, but we just wanted to give you a taste of it this year. All right. So multiplies turn into adds. By the way, what do you think divides turn into? Subtracts, just as easy as you think. All right. So I think that's enough review on logs. Now, to leave you a little bit of work time, I got to get through the other kind really quick. Yes?
What about the problems where there's like a 1 in the argument?
Okay. When you won the argument, there are other patterns. I wasn't going to go through all of them, but I'll do that one. When you've won the argument, you get nothing. And here's why. If I put, I don't know what the answer is. I put an x. I go 2 to the x has to equal 1. And the only way that works is if x equals 0. So if you have a 1 in the argument, you get 0 or nothing. You are correct. That's another pattern. All right. I'd say the most common pattern, if you're talking patterns, is that one. If those two are the same, like x and x, then the answer's got to be the exponent on there, which is 3. So this one just equals 3. If these two are the same, the base is the same, and therefore the answer's already there. The answer is not log equals 3. The answer is just 3. All right, now I got to talk about the other chapter, which is linear programming. Do you remember how to graph something like this? Y equals 2 plus 3x. It would be, oh, that's the y-intercept is 2, has a slope of 3. There, that's the graph. Well, what if I change it to less than? Remember how you shade those? And if it's a less than, you shade which way? Under it. Does that ring a bell? Remember doing that? All right. So if I was going to have you sketch a feasible region, and I'm going to have you graph a couple things. Y is less than or equal to 2x minus 3, and y is, let me think now. Actually, I'm going to make it greater than on that top one. Y is less than or equal to, let's say less, just less than. No, I'm going to stick with less than or equal to. Otherwise, I won't have a feasible region. So I'm going to cross, and then I'm going to go like, make this x plus 5. And then I'm just going to say x is less than or equal to 8. See if you can see where all of those cross. Remember that the corners are the only things that are likely to be the answers. The feasible region is the place that's all shaded in. I think if I did this right. Oh, one more thing. Y has to be greater than 0. That's an important one because it'll keep it shaded on the one side. And then the other common sense constraint is that x has to be greater than 0. That keeps you from having negative answers. Remember how if these are profits and numbers of widgets that you're making at your little factory, that's what a typical question is. Like, they're manufacturing motorcycles and Jeeps. And anyway, you can't manufacture negative motorcycles or negative Jeeps. That's why we have to keep those common sense constraints in there. All right, so here's how these should have looked. I'm going to graph this one where I start with -3. I put a dot, and it's got a slope of 2. How do I know that's 2? I don't have graph paper, so I can just kind of fake it. But I rise 2 and run 1. Rise 2, run 1. Rise 2, run 1. And actually, that one will be a little higher. There we go. And you just keep rising 2 and running 1. That's how slope works. Then I'm going to see where the other one crosses through. Y is less than, okay, wait a minute. This one was greater than that, so I got to shade above it. Let me go so far. Oh, nuts. I'm sorry, I missed something. I needed a negative right there because that will make that slope go down. Otherwise, you would have graphed it like this. And you did it right if you did this. But then they aren't going to intersect nicely because they're both shading up. I meant for it to, actually that'll work. That'll work. I don't have to make it negative. If I do make it negative, do you get what happens? It goes down like this. But I don't have to do that. I can leave it the way it was in the first place. I apologize. Okay, so now I'm going to graph above this. You're right. It's below that one. Man, comedy of errors today. Okay. Okay. Here we go. Shading underneath it. Whew. Okay. Now, do you get why I, at the last second, added in these two? Because I didn't want it to go below this line. I wanted it to stay above that line. and I wanted it to stay inside of here, that kind of like captures it in so that this is your feasible region. What line did I not graph yet? Less than or equal to 8. So then I go to 8, wherever 8 is here, and draw a line straight down. Now, because I haven't done this on graph paper, it's very hard for me to tell whether or not that line even intersects with the feasible region. But if it does, it cuts it off and has to be to the left of it. Y is less, or Y is greater than 0. That's this line. Nope, wait a minute, that's this line. That's the x-axis is where y is greater than 0. So that was me shading right here. So this one is the y-axis, so its x is greater than 0. And that's what's shaded this way. It's not that hard. It really isn't. The x-axis is y equals 0. The y-axis is x equals 0. Okay, once you get it all shaded in, this spot, this spot, this spot, or this spot are the, man, those aren't that clear. I'm going to make them red instead. Maybe that'll show up better. I don't know. There we go. Those spots are your possible answers. And you stick those in to the optimizing equation. They'll give you that separately, and that'll be something like, by the way, in this context, the x is like motorcycles and the y is like Jeeps. And they might say, we make $1,000 profit on every Jeep we sell, and we make $500 profit on every motorcycle we sell. Then the question would be, which of these makes us the most money? Do you get that if you sell nothing, you're not going to make much? So that one would be right out. Of these, aren't you assuming that it's probably either this guy or that guy? Okay, then you'd have to compare at least two to see which one gives you the best. And how do you know if it gives you the best? Well, if I make more money with the Y's, I want one that has more Y's than the other one. Do you get this one that has a lot of Y's? It's very high on the Y-axis. It's the highest Y we have, so it's going to make us probably the most money. But we would take this point, whatever it is, you know, like 6, 8, or whatever that spot is, and we'd stick it into our little profit equation, which would go like this. 1,000 for every Y plus 500 for every X gives us our profit. And you'd stick in the X's and the Y's and figure out, well, this spot here would give me this much profit, and that spot would give me that much profit. That's just a quick reminder of how that section works. To be able to give you some work time, I have to stop now. That's all the review that we have for today.